Hello class, we're going to have our last lecture on research methods. It's really been a journey, quite an interesting one, and I hope you have really enjoyed every bit of the lecture. Today brings the climax of the lectures, and today being the end, I'm going to walk you through testing for associations. Initially, we did causal inferences. What causes what? What risk factor causes a particular disease? But now, we are going to look at associations, the chi-square. Example is, when you are a black man, many people think that when you go to the US, being black is associated with criminality. It's associated though, but we are not saying that the black color or the black race are predisposed or being black causes somebody to be criminal. No. But because of previous experiences and exposure and the criminal record in the US, we have a lot of blacks engaging in criminality in the United States of America. So they say that, oh, being black is associated. But we are not saying your black color can cause you to be a criminal, because some of us are blacks, but we are not criminals. So we are just testing for association, but we are not saying, we are not inferring causation. We are not inferring causal inferences, or we are not establishing causal inferences by saying that being black causes you to be a criminal. No. But we are just associating that, oh, if you are from the Day Ayus family, then you are likely to be a footballer. We are not saying that your father being a footballer will predispose you to become a footballer at all costs. We have footballers whose children are not footballers, but we are just saying that the percentage of footballers whose children are footballers are many. So we end up by saying that your father being a footballer or being a footballer is associated with what? The occupation of your father, or what you become will be associated with what your mother and your father are, because pastors are giving birth to pastors, doctors are giving birth to doctors, laboratory practitioners are giving birth to laboratory practitioners, nurses are giving birth to nurses, meaning that there is quite an association, but we can't establish a cause for this. So by this, we want to go to classroom to really augment our knowledge on association. Thank you very much. So incidence rates of outcome. So you are all familiar with this table. That is the 2 by 2 table. We say 2 by 2 because we have what? One box here, one box here, another box here, another box here. So the rows are what? This is the row, this is another row, and the columns are, this is one column, this is another column. So it's a 2 by 2 table. 2 columns, 2 columns, 2 rows. So it's a 2 by 2 table. So disease status. Those having the disease we attribute them with what? Yes. And those not having the disease, we say they are no. Those who are exposed to the risk factors that cause the disease, yes. And those who are not exposed, no. Okay. So we have the exposure as the row, the disease status as the row, with the exposure, yes, and no non-exposed, we also have it here. So the study cohort is the first row, and the comparison cohort is the second row. 2 by 2 table. So we have the outcome. Anytime you see outcome is the disease. So the outcome present is the disease present. Outcome can also be mortality. Like I said in previous lecture, outcome can be morbidity. Morbidity is the disease. Mortality is also death. So outcome can be death or disease or death. And the outcome absent means the disease was absent over here. So risk factor present. The risk factor, those who were having the risk factor present or were exposed, and those who were not exposed are this row. So exposed are this row, unexposed are this row. So there were people who were exposed and they had the outcome or the disease. Others were exposed but they didn't get the outcome. Some were also not exposed to the risk factor but they had the disease. Some were not exposed to the risk factor and they didn't get the disease. So if you want to find the relative risk, like I showed in previous lectures, repetition of the things we have already done is supposed to cause you to have much more understanding on the subject. So relative risk, we have, this is how we calculate relative risk. We have A over A plus B, that's the total. That's A over A plus B. Then divided by C over C plus D, that is C over C plus D. This gives us the relative risk. And relative risk is for longitudinal studies or cohort studies, whereas odds ratio is for case control studies. So this is how we calculate odds ratio. Odds ratio is what? A over B, that is this A over B, being divided by C over D. And A over B is what? The incident. A over B is what? We have A over B and C over D. Okay, so A over B is the odds of exposure in cases, whereas C over D is the odds of exposure in controls. I repeat again, A over B is odds of exposure in cases, whereas C over D is odds of exposure in controls. So we have A over B, C over D. We can also calculate the odds ratio by just cross multiplication. So A multiplied by D will give us the numerator, and C multiplied by B will give us the denominator. Okay, let's go back to the relative risk. Relative risk is defined as what? A over A plus B. And A over A plus B is the definition for incidence of the disease in the cases, whereas C over C plus D is the incidence of the disease in the controls, because controls don't have the disease. Okay, so let's continue. So in the incidence among exposed is A over A plus B, like is here, A over A plus B. The incidence among non-exposed is C over C plus D, like here, C over C plus D. So by this we calculate the relative risk. So the relative risk will be defined as incidence of disease among exposed. The incidence of disease among non-exposed, that is A over A plus B divided by C over C plus D. That is the relative risk. This is what we are calculating, relative risk. So let's go to the odds ratio calculation. Like I said, A times D divided by C plus C times B, or odds of exposure for cases. That's A over C divided by the controls. You have seen the controls here, so B over D spells out the controls. So B over D is the controls. So odds ratio also estimates the relative risk. Okay, so odds ratio is for case control studies. But some of the time you can even use it interchangeably, nobody will arrest you. So looking for confounding. Since most health outcomes have multiple contribution causes, There are many possible confounders. For example, a study looking at the association between obesity and heart disease might be confounded by age, diet, smoking status, and a variety of other risk factors that might be unevenly distributed between the groups being compared. So we say that confounding variables like age, diet, smoking status, and a variety of other risk factors must be unevenly. They shouldn't be equally distributed. They should be unevenly distributed among the cases and the controls. So if you are having age, then the cases should vary based on the age compared to the controls. So if you are having ages of laboratory personnel who are having hypertension. So if you have 200 lab personnel with hypertension or blood pressure, high blood pressure, that's increased blood pressure. These are males. And you have another 200 females lab personnel with increased blood pressure. What we mean over here is that age is a confounding variable for blood pressure. So if you have these cohorts or these cases, if you have these two comparison groups, then considering ages, you should have age range from 20 to let's say from 20 to 35. These are age group, and this one also should be what, let's say 35 to 45. So this one should be 25 to 35, and the female should be 35 to 45. You see that the ages are not equal, so age becomes a confounder. Because if the ages were equal, they will cancel out each other. So the confounding influence will be cancelled out. That's why when you are doing a study, when you start your project work, make sure that if you are working on diabetes or any condition, if you pick 200 people for controls and 200 people for cases, the cases and the controls should have the same age range. They should have the same age range. They shouldn't have different ages. If the age ranges are different, the age becomes a confounder. So diet status, age, smoking status, and a variety of other risk factors might be uneven. They should be unevenly distributed, because your cases and your controls, their eating habits should be different, their smoking status should be different, and the variety of other risk factors should be different for them to qualify as confounders. So age as a confounder. It is well known that the risk of cardiovascular diseases increases with age, and BMI also tends to increase with age as well. Could any or all of the apparent association between obesity and incidence of cardiovascular disease be attributed to age? So obesity is a risk factor or exposure to what? Cardiovascular disease. It's an exposure or risk factor to cardiovascular disease. But does age associate with obesity and the incidence of cardiovascular disease? Is age a confounding factor? We are yet to establish that. So confounding is a distortion, inaccuracy in the estimation of measurement of association that occurs when the primary exposure of interest is mixed up with some other factor that is associated with the outcome. There are three conditions that must be present for confounding to occur. 1. The confounding factor must be associated with both the risk factor of interest and the outcome. The confounding factor must be distributed unequally among the groups being compared, and a confounder cannot be an intermediary. It cannot be found in the causal pathway. The confounder should not cause the disease. It should rather associate with the exposure to cause the disease, or the disease itself should be associated with the confounder. So let's see, in a hypothetical data set provided below, subjects who were 50 plus were more likely to be obese as compared to younger subjects. So we want to establish whether age is associated with what? Obesity, and also whether age is associated with cardiovascular disease. So let's see, we have developed a stratum. We have stratified the analysis. So we want to see age. Those who were greater than 50 years old were obese, whereas those who were less than 50 years old were what? Were also obese, but their frequency is lower than those who were above 50 years old. So those who were older, the aged, had a higher frequency of obesity compared to the younger. The aged have 200 people being obese, while the younger who were obese were only 100. So when we calculate the odds ratio, the odds of becoming obese were the relative risk of becoming, or the incidence of obesity in the younger participants or subjects was 200 over 200 plus 200, or 200 over 400, being the incidence of obesity in cases. That's 200 over 400, giving us 12.5. The incidence of obesity in controls, that is 100 over 500, being 0.167. So when we calculate the odds ratio, we are supposed to get okay, so let's look at this example. So we have obese being 46, not obese being 60. That's those who are having incidence of cardiovascular disease. And we know that the obese were only 300, and those who had cardiovascular disease were 46. But the not obese were more. They are more than 2 times of the obese. They were 700, and the incidence of cardiovascular disease among them was only 60. So here we are considering their frequencies. We are considering their percentage, cumulative percentages. We realize that those who were obese were only 300, and those who had the disease among the obese were 46, while those who were not obese were 700, and those who did not have the disease among those who were not obese were only 60. So the cumulative incidence of cardiovascular disease in obese persons is 46 over 300, which is equal to 0.1533, and the cumulative incidence in non-obese were 60 over 700, or 60 over total, which is 0.0857. Okay, so we calculated the incidence of cardiovascular disease in the obese and that of cardiovascular disease in the non-obese in order to be able to calculate the relative risk. So relative risk is incidence of cardiovascular disease in the obese, which is 0.1533 over incidence of cardiovascular disease in the non-obese, 0.0857. So 0.153 divided by 0.086 is equal to 1.79. So this is the crude odds ratio or crude relative risk, which suggests that obese persons are 1.79 times as likely to develop cardiovascular disease compared to the non-obese. Okay, so however, it is well known that the risk of cardiovascular disease also increases with age, and BMI tends to increase with age as well. Could any or all of the apparent association between obesity and incidence of cardiovascular disease be attributable to age? We want to establish whether age is a confounder as to whether it's associated with BMI, which is a risk factor for cardiovascular disease, and cardiovascular disease itself, which is the outcome. So if the obese group in our sample is older than the non-obese group, then all or part of the increased cardiovascular risk in obese persons could possibly be due to the increase in age rather than their obesity. And if age is another risk factor for cardiovascular disease, and if obesity and not being obese persons differ in age, then our estimate of association between obesity and cardiovascular disease will be overestimated. What we are saying in the last paragraph is that if age itself is a risk factor, and if obesity and non-obese persons differ in age, then because age is a risk factor, it's a causative agent for cardiovascular disease, then age itself, and we are using it as a confounder, then it will overestimate the effect we are going to get, or the odds ratio, because of the additional burden of being older. So the age will cause an overestimation of effect, or the odds ratio will be higher due to age, because age is not acting as a confounder, but it's now acting as a risk factor. But that is not what we want to establish. So we want to establish, we want to do a stratified analysis. So we take only obesity alone, and when we take obesity alone, in this data set, subjects who were older than 50 were more likely to be obese. That's 200 over 400. That's the incidence of obesity in those who are aged. But comparatively, the younger ones, that's aged less than 50 years, had only 100 obesity. So 100 over 600 gives us 0.67. So you realize that the relative risk is higher over here, 0.15, and here it is 0.167. So the incidence of obesity is the exposure, and that is what we are looking at. The obesity is what? Exposure. So we want to establish exposure status. We want to establish whether age has influence on obesity, meaning that if you are older, will you become obese, and if you are younger, will you become obese? And we saw that being older rather predisposes you to obesity compared to being younger. Being younger gives you, if you are younger, you will not be predisposed to obesity, but if you are older, you will be predisposed to obesity. Let's look at the association between age and cardiovascular disease. The older you get, the more likely you are going to get hypertension, which is as a result of cardiovascular disease. So, in addition, older subjects were more likely to develop cardiovascular disease. The older you are, your higher incidence of getting cardiovascular disease. So we have 65 over 400, giving us an incidence of 0.1625. Then incidence among the younger ones, that's less than 50 years, we have 45 over 600, giving us 0.075. Thus, age meets the definition of a confounder. It is associated with the primary risk factor and the outcome. So we can see that from the variables we've gotten so far, age is associated with what? Because the older you are, look at over here, the incidence in the exposed is 0.1625, which is higher than the younger ones. The incidence in the older, incidence of cardiovascular disease in the older subjects, 0.1625, is higher than the incidence in the younger participants, which is 0.075. The same way, the incidence of obesity in the older is 0.5, which is higher than incidence of obesity in the younger, which is 0.167. And obesity is the risk factor. So age is associated with both obesity, which is a risk factor or exposure, and the outcome, which is cardiovascular disease. So in order to be a confounder, the extraneous or external factor must be associated with the primary exposure of interest and also be associated with the outcome. One approach would be to test this association using a test of hypothesis. And our primary interest was in the association between obesity and cardiovascular disease. But we were also concerned that age might be a confounding factor. The chi-square test is what we are going to use. And we will use the chi-square test to establish whether there is an association between age and obesity. Also, is age also associated with cardiovascular disease? So obesity is the risk factor, and age and the cardiovascular disease is the outcome. So the predictor or exposure or risk factor is obesity, and cardiovascular disease is the outcome. So the formula for chi-square test is what? The chi-square symbol, summation of observed minus expected over expected. Observed minus expected into bracket squared over expected. This is the chi-square formula. So the numbers in the bracket indicate the expected values under the null hypothesis. So you can see the null hypothesis is what everybody knows, the common knowledge. The null hypothesis is what everybody knows. Everybody knows that if you drink an acid, you will die. But somebody will say that, oh, if you drink an acid that has been mixed with lemon, you will not die, because the lemon will break down the acid compounds into it will break down the acid molecules or compounds into an unharmful metabolites. So that is his research hypothesis or alternative hypothesis. Whereas the common knowledge that when you drink acid you will die, that one is the null hypothesis. But the research hypothesis is what the researcher has done and his findings and his conclusions that defeats what we already know is what we call the research hypothesis. So as a researcher, you are observing, this is what the researcher observes, and what is in the bracket is that is the null hypothesis or what has been established. Then what is not in the bracket, that is the 100, 500, 200, 200, is the findings of the researcher or what the researcher is observing. So we would like to go to the whiteboard and do some small calculation and come back. So taking the obese, this box, we want to calculate the chi-square in this box. We have to calculate it for this box, this box, this box, this box. So when we calculate, I'm just going to calculate the first two boxes, then we continue. So 100 is the observed, and 180 is the null hypothesis, or the expected, or what we already know. Okay, so let's go to the whiteboard and do this calculation. So we start by saying that chi-square is defined as the summation, the sum of, into brackets, observed minus expected squared all over expected. This is equal to, the observed we are having is 100, and the expected is what? Let me go and cross check. Observed is 100 and expected is 180. So 180 squared over 180. This gives us 80 squared over 180. This gives us 80 times 80 over 180, giving us which gives us 35.56. Because realize that the observed is equal to 100, expected, which is what we already know. So we are expecting it because we already know that if you drink acid, you will die. So that is our null hypothesis. That is 180. So when we compute this, we'll end up getting 35.56. But the formula is for summation. So sum of all this. So we have done this for only the first box. We've done this for only the first box. So when we continue the same for the second box. So when we did it for this first box, we had this. When we do the same for the second box, we will get this. Third box, we will get this. Fourth box, we will get this. So when we get this, we add everything to give us 126.98. So let's go and do the calculation for the second box. So I'm just cleaning the entries so that it will be easier for us to remember. So here we are going to now compute the the observed and the expected for cell 2 or box 2. Okay, so let's see. So 500 is the observed, and what we expect, or the null hypothesis, is the 420. So 500 is observed. Observed is 500. Expected is 420. Okay, so we have observed, which is what, 500, minus expected, which is 420. This also gives us 80 squared, and 80 squared is what, 80 times 80. 80, and the expected is what, 500. Expected is 420. 420. Expected is 420. 420. 420. So when we compute this, we're going to end up by getting, we're going to compute 15.23. You can pause the video or the recording and try your hands on the calculation and continue. So this is the calculation, and this is what we are getting. So when we go back, we have the second box. When we calculate 500, 420, we get 15.23. When we add everything, we get 126.98. Meaning that there are 2 rows and 2 columns. We have 2 rows here, 1, 2, and the obesity column, 2 columns. So we have to calculate the degrees of freedom. So the degrees of freedom is what? Anytime you hear degree of freedom, if you give you the freedom to be 5, you subtract by 1. If you give you freedom to be 10, degree of freedom to be 10, you subtract 1 from it. You give degree of freedom to be 20, you subtract 1, giving you 19. Degree of freedom to be 100, you subtract 1, giving you 99. So here, the degrees of freedom is that we have the age with the age column. Looking at the ages, we have 2 rows, 1, 2. So we subtract 1, so the rows are 2. So we subtract 1 from it to give us 1. Then the columns are the obesity column. That's obese, not obese. There are 2 columns. 2 columns. So that one too gives us 2. So we subtract 1 to get the degree of freedom. So in the end, for the columns, we have 2 minus 1, and the rows too, we have 2 minus 1. So 2 minus 1, 2 minus 1 gives us 1 times 1, giving us 1. So when you look at, we have a statistical table that we compare the results to be able to extract our critical value. So for degree of freedom is equal to 1, and at an alpha value, whenever you hear alpha value is the same as what? The confidence limit. What do we call it? The level of significance. So when we see alpha value, when we say the significance is at 10%, 10% level of significance, 10% level of significance is the same as what? Alpha and omega. Alpha value. If it is 5% level of significance, it is also called alpha value. So anytime you hear level of significance and they mention the percentage, it is called alpha value. So over here, So we have, so when we look at the statistical table, degree of freedom, that 1 times 1 gives us 1. At an alpha value of 5%, the critical value you will see from the statistical table is 3.84. And we can see that 3.84 is far less than 126.98. So the chi-square value that we had was the chi-square gave us 126.98, which is far greater than 3.84. So we are going to accept the fact that our results that we are getting is different from what is already known, or the null hypothesis. So our finding is correct, and it has defeated what people already know. So we want to conclude by saying that, therefore, we reject H0, because 126.98, which is our chi-square value, is greater than the critical value. Then the critical value represents the null hypothesis. So we reject it because what we are getting from our study or our research defeats what people already know. Because what people already know, our findings have conquered it. So that is why the chi-square value is higher than the chi-square value of what people already know. So we have statistically significant evidence at the confidence interval or alpha value of 0.05 to show that the null hypothesis is false. Age and obesity are not independent. That is, they are related. So the more you age, the more you become obese, the more you become so fat, the more your weight increases, and that is what predisposes you to cardiovascular diseases. So we say p-value is less than 0.005. But if p-value were to be greater than 0.005, then we will say that, oh, what we found in our test is the same as what people already know. So we accept the null hypothesis. We refuse to reject it. We accept it just like that. Let's take another example. We can also use the same procedure to assess whether age is associated with incidence of cardiovascular disease. So in the first stratum, we use age to find out whether there is a difference in whether age difference, or whether when you age, or whether obesity is associated with age. But now we want to also determine whether cardiovascular diseases are associated with age. So the data for this association are shown below, with the values expected for the null hypothesis shown in the parentheses. So we are going to do similar calculation. So when we calculate observed minus expected, so 45 minus 63.6 all squared divided by 63.6, we will get what? 5.44. When we do the same calculation, we will get 0.64, the same calculation 8.16, and the same calculation for the fourth box, we will get 0.97. When we add everything, it gives us 15.21. And once again, degree of freedom for the row, which is what? The rows are 2, 1, 2. So we have 2 minus 1. Then the degree of freedom for the column is 1. We have 2 columns for the cardiovascular disease. That is 1 and 2. So the exposures are 2 rows, and the disease or the outcome are 2 rows. That's incidence of cardiovascular disease and no cardiovascular disease. So 2 minus 1 gives us 1. And then for the column also 2 minus 1 gives us 1. So we have 2 minus 1, 2 minus 1 giving us 1. For degree of freedom is equal to 1, and a 5% alpha level of over here we are going to reject the null hypothesis, because 15.21 is far greater than 3.84. So end by saying that therefore some of the association between obesity and incidence of cardiovascular disease can be attributed to age. So age over here is very important. because it is associated. We can see over here that in the obesity, over here we saw that age was associated with obesity. At the same, and the obesity is a risk factor or the predictor, is the exposure for cardiovascular disease. If you are not exposed, if you are not obese, it's not likely you get a cardiovascular disease. So age was associated. The more you age, the more you get obesity. The same way, cardiovascular disease was also associated with age, meaning that the more you age, the more you are prone to get cardiovascular disease. So the confounder, which is age, was unequally distributed among cardiovascular disease, which is the outcome, and obesity, which is the exposure or the risk factor. Okay, so we would like to take another example. So looking at age, when we stratify it, age less than 50, age greater than 50, we have what? For obesity, when we stratify age for the obesity, we get what? 1.43. Those who are younger than 50, we get 1.43. Those who are older than 50 years, we get to 1.44. So 1.44 is greater than or higher than 1.43. So we say that age is associated with what? Cardiovascular disease in the obese. So if you are obese, you have cardiovascular disease because you are older. So you realize that those who are older, above 50 years, they were associated with higher odds, higher relative risk of getting cardiovascular disease, while the younger were associated with lower relative risk of getting cardiovascular disease. So determine whether a variable is a confounder. There are different methods to determine whether a variable is a confounder or not. As you have noticed, some investigators perform formal tests of hypothesis to assess whether the variable is associated with the risk factor and with the outcome. As shown in the example above, determine whether age is a confounder for the association between obesity and cardiovascular disease. So here we saw that age is a confounder because you see, the more you age, the relative risk becomes higher than the younger ones. Some investigators perform formal tests of hypothesis to assess whether the variable is associated with the risk factor and with the outcome, as shown in the example above. Therefore, determine whether age is a confounder for the association between obesity and this is what we have already established. Other investigators do not conclude statistical tests. Other investigators do not conduct statistical tests, but instead inspect the data. So some even don't worry themselves to conduct the tests we have conducted, but they just inspect the data, and if there is a practical, important, or clinical meaningful relationship between the variable and the risk factor, and between the variable and the outcome, regardless of whether that relationship reaches statistical significance or not, the variable is said to be a confounder. So over here, we realize that 1.43, the relative risk of 1.43 and 1.44, when you do the adjustment, you realize that it's a confounder. But some investigators just inspect. They just inspect the data, whether there is significance or not. They don't look at significance. They just inspect the data to establish whether there is a confounding influence or not. So our last slide. Still, other investigators determine whether there is confounding by estimating the measure of association before and after adjusting for a potential confounder. A change in the estimated measure of association of 10% or more would be evidence that confounding was present. But if the measure of association changes by less than 10%, there is likely to be little or, if any, confounding by that variable. So using the example above, the adjusted risk ratio will be about 1.43 and the good risk ratio before adjustment to 1.78. So over here, let's look at, over here we have, this is the crude. Crude means that you have adjusted or you have stratified it. So we stratified our findings based on age, less than 50 and greater than 50. And we had what? 1.43 to be those who are less than 50, and they are almost 1 so we just chose one of these relative rates and computed. But the crude one was what we did for both. We did analysis for both less than 50 and greater than 50, and we had our finding or our results is, so the crude one we had 1.79. So when we had the crude one, when we know we have the crude one, we have the obese and non-obese incidence of cardiovascular disease, but we didn't adjust for confounding based on age. So that is why it is crude odds ratio or crude relative rates. So we had what? Our relative rates to be 1.79. That's the crude, because over here we didn't take age into consideration. Age was absent over here, but it is the confounding influence of age that gave us our results, abnormal results. But in the crude, we don't take into consideration the confounder, because we don't even know what the confounder is, whether there is confounding or there is no confounding. But when we put them into stratum specific strata, we arrive at, when we stratify them, we arrive at 1.43 and 1.44. So we just choose for the control 1.43. So 1.43, we subtract it from the crude. So the crude gave us 1.79, but we are using 1.78 over here, minus 1.43 divided by 1.43. So this one gives us 1.78 minus 1. We are just finding the percentage change. So 1.78 minus 1.43, all divided by 1.43 gives us 24.5%. So because it is greater than 10%, there is confounding. But if the result was less than 10%, I would have said that there is no confounding. But because the difference is greater than 10%, the difference between the crude odds ratio and the adjusted odds ratio was greater than 10%, it gives us a confounding influence. So age was equally associated with the risk factor. The age was unequally associated with the risk factor and the outcome. So we want to end our lecture on confounding here. Lecture 2 will be on, I want us to have a lecture which I will take you through what an independent variable and a dependent variable is. So stay tuned for the part 2 of this lecture, because the independent variable, dependent variable, you'll be meeting a lot of them in the exams questions. So please stay glued. That one will be about 5 minutes to 10 minutes lecture. So stay glued, stay tuned for it. Thank you very much for your attention.